we are finishing off today hypothesis testing, and we're looking at hypothesis testing in the context of the difference in two proportions. And I'm going to do three examples, start to finish. So we're going to look at, the first one would be a very common usage for this technique, and that is in a clinical trial. So here is my story. We've got two drugs, the old drug, right, and the new drug. And we are interested in, does the new drug do a better job, right? That's the classic thing that you would go out there and try and prove. The old drug is called the control drug, and the new one would be called the experimental. So population 1 is going to be the old drug, and population 2 is going to be essentially the new drug. And we are going to, in this story, do a double-blind test. And this particular drug is meant to reduce the seizures that people get when they, what is it called? Epilepsy, right? The seizures that people get when they get epilepsy. So basically, from what I know of epilepsy, not that I have it, but essentially what happens is that there's a chain reaction in your brain, and like everything is shooting information all over the place. It's a bit like going zzz, all over the place, and that causes seizures in people. And there are drugs where they can subdue the likelihood of that happening. So people take this old drug, and in this, there were 200 people, and the success rate was 71%. So what that would mean depends on what you call success rate. It might be that a success rate is less than one seizure, well, less than two seizures, right? One or no seizures a month, right? Something like that. And the new drug, 500 people in that one. And in this case, you got a 74% success rate. So if you were the pharmaceutical company, you would be quite happy with that. But the FDA doesn't take raw data because they know all about statistics. So you would have to take this data. In fact, you don't do it. The pharmaceutical companies don't do this. They outsource it to an independent company that deals with processing it. So we are going to set up a hypothesis test to see if there's evidence that the new drug is better than the old. And that's a reasonable test, right? Is there enough evidence to show that the new drug does a better job, right? A better success rate than the old. In this story, we are going to do a significance level of 0.01. So first thing we're going to have to do is set up the null and alternate hypothesis. One of the nice things about the difference in two proportions hypothesis test is that isn't not always the null hypothesis, no matter what the story is, right? And then the alternate. There is three possibilities. Should this be bigger than 0? Right? So you read this and you say, would that be bigger than, not equal to, or less than? Old drug, new drug. what would you expect the difference to be? Greater than, less than, or not equal to 0?
Be less than 0?
Right. If you look at the data, do you see that if you take this guy 1 and subtract this guy 2, isn't the answer going to be negative? That would be a clue. Secondly, don't you want the thing to be better? And in this case, better means that this is bigger than that. So that comes to the same conclusion. So we are hoping to find that the difference is less than 0, because that means this is small and this is big. That's essentially what that means. We have the next stage of the process is eventually to get, I think I call it the Z-score, they call it the test statistic. Now to do that, there's a whole load of information. Let's start with finding P1 hat, take away P2 hat, which is 0.71, take away 0.74. And that's good news. It is negative. We were hoping that, but it's not a very big negative, is it? It's only a few percent, but it is negative. We have to find the standard error, and that ends up being quite an ugly formula. But good news is that's what calculators are for. So 0.71, 0.29 over 200 added to 0.74, 0.26 all over 500. So square root of that guy times that guy divided by 200 plus this fella, 74, 26 divided by 500, and we get 0.038 to 3 decimal places. Now, our goal right now is to find the Z-score, the test statistic. But to be able to do that, we needed to know this guy and this guy, because the test statistic, that name down again, means the Z-score. That's just another name for it. And the formula for it is P1 hat, take away P2 hat over the standard error. And that's why we calculated these guys. So the Z-score is equal to negative 0.03 divided by 0.038 and negative 0.03 divided by 0.038, and we have negative 0.79 to 2 decimal places. Now we're going to finish this calculation, but I already kind of know that it's not going to be significant. How can I tell just looking at the Z-score that we're not going to be able to say the new drug does a better job than the old drug? What about this value? Z-scores need to be extreme to get evidence. An extreme typically is at least in the high 2s, right? 2 point this or minus 2 point that. 3 and 4 are even better, right? A z-score of 4, or I think we did one yesterday, it was like 6.8. Those are really great data, right? But here, ain't gonna happen. But we have to go through the process. We're going to get the most important number in a hypothesis test is the p-value. And the p-value is the probability that you get a z-score greater, less, or just not equal to that. And that guy there tells me what I'm looking for. So it's less than that number. Right, not greater than that number, less than that number. And what I then do is I go over to salt, which I'm doing right now as we speak. And we'll do that calculation just to remind you how it works. Right. So you should be looking at distribution calculation. Normal distribution, 0 and 1. We are looking for a less than and a less than negative 0.79. And the p-value is here, right below it. It's basically that area there. That's the probability is in terms of an area. So in this case, we have a 0.21. That's pretty much the only part of that process that we needed to go to solve. That's that bit of the process finished. Now we do our test. Our test will be, is the p-value that we just found less than the significance level alpha? In this case, is that guy less than 0.01? That answer to that is no, it's not. When the answer is no, you will say, this is your conclusion. Not enough evidence. To reject H0. In English, there's not enough evidence to prove that the new drug does a better job at reducing seizures due to epilepsy than the old drug. Now, not enough evidence is not the same thing as saying it doesn't do a better job. It just means we can't prove it one way or the other. So that's a pretty boring kind of conclusion. You might have well have said, well, we just spent $2 million on a big clinical trial, and at the end of that clinical trial, we haven't proved to the FDA that we've got a better drug. And so the FDA are just going to turn around and say, you ain't allowed to use it. There's no reason for us to put another drug out there that you haven't successfully shown to us does a better job. I mean, it could have side effects. You won't even know what they are. We're not going to risk it. And so the pharmaceutical company chalk that down as a loss and just don't bother. Or if they really, really, really think that it is a better drug and they just got a bad random example, couldn't they take this and maybe up it to 5,000 and 2,000? I mean, really spend a whack of money on it. Because if you make these larger, won't you, if there is any evidence that this is better, won't it show? It will eventually show, even if you were very unlucky, right? If you have huge samples, luck has nothing to do with it anymore, right? As a quote that I remember from a golfer who was playing against a guy, and this professional golfer was getting lots of shots and they would bounce and would turn and go near the hole or in the hole. And the guy next to him went and said, "You're just lucky, aren't you?" And the professional golfer went and said, "You know, the more I practice, the luckier I get." So the more times you do it, luck disappears. Yes, that's what I'm saying. Are you comfortable with the process? Because that is the key. If you follow what I've got right now, and you make sure that the information you get is fair and unbiased, then any research magazine or university would be able to take your data and understand that it's valid and agree with you. Well, that's my first one, and that's an example of a clinical trial. Check that off our little list. And that one happened to have no conclusions. Okay, so my second story is about road accidents. And the government Department of Transport is interested in do roundabouts reduce accidents as opposed to having a set of lights. So, you know, the kind of set of lights, you go like this. Actually, let's change it, not from a set of lights, that tends to stop people on the tracks. Do you know those four-way stops where you have to wait for the guy on the right to go before you go, right? One of those, everybody stops, but there's an order. Or, oops, I'm sure I can't do roundabouts very well. Or you use a roundabout. I am very comfortable with roundabouts. Back home in Scotland, there are many more roundabouts than there are these kind of stops. In fact, there are very few places, except maybe out in the countryside, where they don't have lights. They build roundabouts. Has anybody tried a roundabout? I think there's about, what, 3 in this area? There's one over in Chico. No. I'm just wondering why you don't use roundabouts. Once you get used to them, they're great. Yeah. So, they pick samples of places that look like this and similar places that look like this, and they collect data, maybe the last, I don't know how long, hopefully 30 years worth of data, right? And here they looked at a sample of 100, and they found out that there was an accident rate of 35%. So over a 30-year period, right, there was some like 35 accidents, right? Like one a year, right? Now, we're not talking fatalities, right? Anything involved the police coming in, fender benders and that kind of stuff. And then they looked at 200 roundabouts, and they found out that for roundabouts, there was a 28% accident rate. So over a 30-year period, there would be something like 7-8 accidents, right, on a roundabout. So they are interested in comparing these two, okay? And we want to find out essentially is, are roundabouts safer? So is there enough evidence to prove that roundabouts are safer? Now, in the way that I've numbered the two situations, crossroads against roundabouts, the null hypothesis is still going to be that one. This is P1, this is P2, right? These are crossroads, these are roundabouts. Greater than 0, less than 0.
Less than 0.
You're saying that this guy, take away that guy, is less than 0.
Greater than, right?
Yeah. Correct. Now, why is that the case when you're trying to prove something safer? It's because of the English language. John is taller than Mary. Mary is smaller than Tom. Isn't that the same information, but one's using a greater than, one's using a less than? So in this story, for roundabouts to be safer, doesn't this need to be bigger than that? You see how it works? So the best way to figure it out is look at the raw data. That tends to tell you, right? You know, if you take this guy and take away that guy, isn't the answer positive? Right. Now, I need the significance level. Let's do a 5%. We should be ready to do our thing. So P1 hat, take away P2 hat. 7% difference in the accident rate over a 30-year period. What would that end up being? It'd end up being about 2 fewer accidents, right, a year. So can you imagine that's something, right? Now, what we're going to calculate next is the standard error. This is the square root P1 hat 1 minus P1 hat over N1, then P2 hat, take away P2 hat over N2. In this case, it's a 35, 65 over a 100, and a 28, 72, 200. So 0.35 times 0.65 divided by 100 plus a 0.28 times 0.72 divided by a 200, and the answer I have is about 0.057. We'll now calculate the test statistic. Should I call the Z-score? P1 hat, take away P2 hat over the standard error. P1 hat, take away P2 hat. And that ends up being 0.07 divided by 0.057. 0.07 divided by 0.057, and the answer I get is 1.22. You comfortable with that? It's pretty much once the story starts, don't the calculations end up being the same? Just the numbers inside them. So we need to find our p-value. And so it's going to be the probability that we get a z-score. And in this case, greater than 1.22. And I'll just do that without me zooming back and forward. So I'm hitting a right tail. I'm putting in a 1.22. And the answer I get was 0.11. So I do my test. And my test is my p-value less than the significance level alpha? And is that guy less than 0.05? No, it's not. So our conclusion is not enough evidence. To reject H0, which is the answer you give every time that happens. By the way, I'm going to make sure the next one is conclusive. But it's not your job to make this work. Your job is, based on the data that you've got, is there evidence here, right? Even if you desperately want something to be true, that makes no, it should have no influence on what you do, right? The calculations, don't they force you to do something? And they force you to get a number, and they force you to use a test, right? You're not allowed to say, well, I think 7% is pretty good, so you've convinced me roundabouts are safer. Or I think a Z-score of 1.22 is big enough. You've convinced me that roundabouts are safer. You see that you don't have any option, right? You have to go through the process. And if the process comes up with not enough evidence, you have just got to accept that you have not got enough evidence. As disappointing as that can be. Are we cool?
Yeah,
Any
one
questions?
question, actually.
Say again?
One question, actually.
Yes.
It was greater than 0 for most of the problem, but that last test you did was less than instead of greater than.
Yes. This here
Yeah.
is always going to be less than, right? The p-value has to be small. No matter what of the three situations you've got, it's always going to be less than, right? So the p-value will be less than, even when it's prove it's bigger, prove it's less, or even when it says prove it's different. This doesn't change. This is fixed.
Okay.
Because essentially the way it works is this p-value has to be tiny, because tiny means it's very, very rare that you got the data you got when this was true. Because it's very rare, we'll assume that that's not what happened. That's the alternate is true. So small p-values are good evidence. And the smaller the p-value is, the stronger that evidence becomes. So that's why this should always be small. And so you want to test it against a fixed value and make it, hopefully make it so that it ends up being conclusive. Now, I don't know, I guess I could find out why people in America, at least on the West Coast, or at least in Washington, I've not driven too much in other places, don't like roundabouts. So before we move on, just because my curiosity is piqued, why don't you do roundabouts in this area? Many. In fact, when I went and said it, some of you went and I thought I got the impression that some of you said, we have roundabouts.
I would say people just aren't used to it. I'm from a city out in Tacoma where there's a few of them, and people who've been here for a while, you just get used to it, you know?
Yeah. I mean, there are rules. Maybe I think the problem is I don't think you are, when you learn to drive in this area, that you are actually taken to roundabouts and shown how you should properly use them. I mean, there are a couple of rules that drive me crazy because I'm used to roundabouts. Is when you approach a roundabout, there's rules about what happens if someone else is on one of the other roads, right? So if I'm coming along a roundabout, let's say I'm coming this way and there's somebody over here coming that way, right? And we both kind of arrive, give or take a second, at that point. Do I go first or does this person go first? What is the rule in America? Well, there you go. You don't even know how to do it. Now, if you come to a four-way stop, isn't the rule the guy that arrives first should get priority? Now, you know that rule, right? That's why you can handle four-way stops. Does anybody know?
Isn't the rule the same at a four-way stop? If you come at the same time as somebody on the right of you, the person on the right goes first?
Not in Britain. The rule is the person to the right goes first. Now, if you arrive and nobody's there, you just go. But if you both arrive at the same time, or give or take, you know, a second, right? So it's hard to say who arrived first. The one on the right goes first, and you might say, why does that person have priority? If this person goes and that person goes, they're going to hit each other. If this person goes, he's probably going to be in front of you. So there's less chance of bumping into people. That's the reason we have that rule. Now, maybe in America, because you're back to front and upside down, you have a totally different rule, which might be first one arrives. It might be the person on the left gets priority, but you have some weird ones. Second rule, when you're going round a roundabout, you are meant to indicate before you leave which road you're going to take. So if I was going to exit on this road, I would do no signals until I got to here, and then I would be signaling that I was going to leave. Do you use that road, that rule, Tanya?
Yes.
Good. Does
Oh, yeah.
everybody that you meet on a roundabout use that rule?
No, God, no, it's awful.
No,
It
they
is
barely use
absolutely
turn
horrible.
signals regularly.
Right? They just don't tell you. Now, that's a big deal, isn't it? Because when you're on a roundabout, it's kind of nice to know that the guy in front of you is going to be leaving, rather than you, is he going to leave or is he not? I just got my roundabout thing. Roundabouts are really cool, but you got to get used to them. I believe in the East Coast, they have more roundabouts. Is that correct? I believe they are. Our third and final story then. We're going to do a before and after advertisement. Right, so made up story. In Scotland, before they had advertisement for a certain brand of whiskey, and then they're going to have after an advertisement campaign. Do you know those campaigns that drive you crazy after a while? You know, the first 2 times you see it, the advert's great. You know, they very often they make them funny, but after 4 weeks of seeing the advert, aren't you? Well, maybe it's just me. Aren't you that fed up with that advert that you would almost not buy the stuff because it annoys you? You ever had one of those adverts that just too many, right? So, advertising company wants to actually find out if their advertising campaign had any significant effect. Did it increase the amount of people who buy their brand of whiskey, or did it decrease them, right, as a percentage of population? So before the advertising campaign started, there was 31% people would buy their product once a month, and that was on a sample of 200 people. So they randomly picked 200 people, and 31% said, yeah, I buy that whiskey about once a month or so. And then they did a big 2-month publicity campaign, buy this stuff, whatever. And after the campaign, they got 39% of people said that they had bought that brand of whiskey. Now, you could say on this data that we were going to do it as a prove that this has gone up, which it has, but this was done before we got the data, because hypothesis testing should be done before you've seen the data. So what we were after is this one. Is there evidence that it changed the use? Right. So is it different, essentially? So the null hypothesis is going to be that P1 was the same. Oops, P1 take away P2 is 0. I was about to put down P1 equals P2, which is exactly the same thing. In some textbooks, they actually do that. And the alternate, has it changed? That one, you do a not equals. Then you would collect your data, and we're going to do a significance level of 10%. So I find P1 hat, take away P2 hat. That's 31. Take away 39, which is negative 0.08. So superficially, would you agree that this particular advertising campaign has improved the sales, right? If you were in that company, you would be really happy with that. You'd say, oh, hey, this is good. You know, that 5 million or 20 million we spent was worth it, right? We got a lot of sales. One of the problems with advertising is that once you stop your advertising campaign, don't things kind of dwindle back? And very often they just dwindle back to the 31% that they were in the first place. So you only get like a minor boost maybe for a year or so. So standard error is the square root P1 hat 1 take away P2 hat over N1. P2 hat 1 take away P2 hat over N2. So 31, 69 over 200. And it's 39, 61 over 500. And I want to see a very small standard error. So here it goes. 31, 69 divided by 200 plus 39, 61 divided by 500. And I got 0.039. So our test statistic, which is called the Z-score, is the difference in the proportions divided by the standard error. And the guy that we got here is negative 0.08. And it's going to be divided by 0.039. And that comes out to be negative 0.08 divided by 0.039. And we get an answer of negative 2.05. Right. Does that look like a decent Z-score? Better than any of the other two, right? I would have much preferred that this answer was higher than that, because when I made those numbers up, I thought an 8% difference would have been enough. But I now know it's not. So here goes. When you want to get a p-value for two-tailed test, which is what you call these, you're going to have to find the probability that Z is less than that number or it's greater than that number. That looks weirder than it really is. So let me show you how you get that guy using salt. You just hit both tails. And the reason why you do two tails in this area is you want to prove it's different. It could be different because it's bigger, right? Or because it's less, right? One side or the other. So you need two tails. And here I'm going to put negative 2.05. I'm getting proved wrong here because I was wanting this to be actually at least a significant answer, bigger than that side. Ah, I am lucky. Yay. I'm bad at judging what p-values are going to be. It's 0.04. That was lucky. Whoa, that was lucky. So I wasn't proved wrong after all. The gap that I made was large enough. So there's our p-value. Here's our test. And it's always going to be p-value less than alpha. Doesn't matter if it's a greater than, a less than, or in this case, a not equal to. This is your same test each time. And we want to find, is that guy less than 0.10? And the answer is yes. So we can actually say there is evidence to prove sales did increase. So the advertising campaign did change it. And in this particular story, didn't they change it by making it increase? It could have changed it, couldn't it, by actually making people less likely to buy the thing. Do you know, if you do a really bad advert, you could put people off it. You know, imagine you were trying to get people to eat hamburgers and you showed them the cows in the field, and then you showed them going into the slaughterhouse and then beef burgers popped out the other side. That would probably put you off eating them rather than wanting you to eat them. So some adverts are really bad. So for the last few moments, let me tell you what's happening in the coming week. That's it, week. We are only 1 week away from finishing. Next week, we will be doing chapter 13, and we'll be looking at hypothesis testing again, but this time not with proportions, but with means.